So I think now we're going to move on to Vichawan Sakulsupich, otherwise known as Print. Print's a PhD student at the University of Cambridge, and she's working on sulfate aerosol formation and its role in the climate. She's also a co-lead of one of our Fresh Eyes on CMIP subgroups, the data access subgroup. But today she's going to be talking about the role of sulfur from human emissions in climate change. Over to you, Print.
Thank you so much, Beth, for the introduction. I'll try to share my screen. The entire screen. Okay. Can you see my screen? Oh, not this one.
Yes, yeah, perfect.
Ooh. Okay, perfect. It's no, I just want to start from the beginning. All right. Everything works now?
Yeah, looks good.
Okay, perfect. So thank you very much for being here today. So today I would like to talk about my PhD work on the role of aerosols from human emission in driving the climate change. So we have heard a little bit about climate change, which is driven by the greenhouse gases, but my work is more on the another type of emission from human. But first, we need to talk about what are aerosols and where do they come from. So aerosols, first, aerosols are like tiny droplets of suspension. It could be solid or liquid that is suspended in the air. And these aerosols, they are so numerous that they can actually affect the climate. So first of all, let's look at this model simulation on like different type of aerosol and how they circulate around the Earth. So in this simulation by NASA, there are different type of aerosol they have simulated. So the orange each one here would be the desert dust in the orange one. So you can see that the Sahara Desert, and then also from the Central Australia. But then we can also see other color of the aerosol as well. We see the blue ones here, these are sea salt aerosols, and the green ones, these are biogenic aerosols, such as like biomass burning or other type of secondary organic aerosols. But our focus today is the white ones here. So these are sulfate aerosols. Sulfate aerosols are what we call secondary aerosols, which means that we don't emit aerosol directly into the air like the Saharan dust, the Saharan dust, but these aerosols are formed in the air from its precursors. For these white aerosols here, these are sulfate aerosols, and their precursors are the sulfur dioxide. Sulfur dioxide are emitted both from the natural sources such as volcanoes, or like from oceanic phytoplankton. But a lot of the sulfur dioxide in the atmosphere are from human activities such as coal burning or industrial activities. Another reason that why we might be interested in studying aerosol is because at the ground level, aerosols could be a health problem. So a lot of us might be hearing about the PM 2.5 problem, which can cause like asthma or any other health problems like lung cancer as well. So that is another motivation for studying the aerosols. But here today, we would be talking about the climate effects of aerosols. As our previous speaker has talked about the carbon dioxide effect on the climate in the historical period, we know that carbon dioxide actually contribute to around 1 to 1.2 degree warming worldwide since the 1750. So this figure is taken from the IPCC report. But other than carbon dioxide, we also know that other gases also contribute to the global warming as well. So other gases such as methane or ozone also contribute to a little bit of the warming. But there is a caveat here. So the other side of the plot is the cooling, and we can see that aerosol actually down the climate. And the problem here is the cooling from aerosol has a very large uncertainty. And this is, of course, a problem because when we want to inform policymakers, we want our prediction to be as small as possible for the protection to be robust. So my work is trying to attribute the change in aerosol relative effect. So how aerosol cools down, how aerosol change the radiation at the top of the atmosphere due to other short-lived climate forces such as ozone and methane, which we know by themselves are greenhouse gases. But because ozone and methane, they are also reactive, they also react in the atmosphere and then change the aerosol relative effect. So how sulfate aerosols are simulated in the model. So the model I'm using today is the UK ESM1, and the data I'm using is from the aerosol chemistry model interconference project, and this also links nicely to my role in the Fresh Eye on CMIP, because most of the data I use is actually in the CMIP archive. So my PhD is mostly based on this archive, and that's why I want to advocate for like more data access. But that aside, let's go back to how sulfate aerosols are formed in the model. In the model, sulfur dioxide is emitted as gas in the atmosphere. It can be biogenic, so from volcano, or it can be from human activities, so from like coal burning and such. And then because SO2 is reactive, it could react in the gas phase with OH to form sulfate aerosols. In this pathway, when SO2 react with hydroxyl radical or OH, it forms into sulfuric acid, which then nucleates into new aerosols. So we are adding more aerosol particles or number to our system. But alternatively, aerosol could dissolve into cloud droplets. So where clouds are available, the aerosol can dissolve into the cloud droplets and react in the aqueous phase. So react in the liquid droplets with ozone and hydrogen peroxide, and these also form sulfate aerosol. But the caveat here is because sulfur dioxide have to dissolve into the existing droplets, they only add the aerosol mass to the existing aerosol. So no new aerosol, but the aerosol just get heavier, like bigger. And then both like all of these aerosols by themselves would change the radiation in the Earth system. So aerosols by themselves directly scatter sunlight. So when we have aerosol in the atmosphere, when the sunlight comes down from the space, it gets scattered back into the space, so there is less sunlight reaching down to the Earth. So that would cause cooling. And we call this the aerosol direct effect. But aerosol also indirectly modify cloud properties. So when we have more aerosols in the cloud, the cloud droplets are smaller and then cloud with smaller droplets tend to be whiter. When we have whiter cloud, these clouds reflect more sunlight back to space, and that also causes cooling. So now let's talk about the model data that I'm using and how these are set up. So I use the UK ASM1 data output from the CMIP experiment. These simulations simulate the transient atmosphere only simulation from the 1850 to 2014. So these are counted as the historical period. So all these experiments, they are designed to attribute the effects of emission change to the system, and our focus here would be on SO2 oxidation and its relative forcing. So if we look at so I'm looking at 4 simulations here in this experiment set. So the first one, the black one, is the SST. So SST stands for sea surface temperature. So let's it's just a way to say that this is atmosphere only and it is not coupled to the ocean. So with the black experiment, we have all of the emission follow the historical trajectory. So everything increases. So methane increases, ozone precursor increases, and adds to the amount of ozone in the atmosphere, and aerosol precursor also increases. But we also have the other colorful experiments which are counterfactual. So these didn't happen in the past, but these are helpful for us in trying to attribute the effect of this emission. So the green one is the HIS SST PI air. So PI stands for pre-industrial. So it means that in this experiment, the aerosol precursors is set to the pre-industrial value, which is the 1850. The same goes for the orange one. So this is PI ozone. So the ozone precursor is set to the 1850 value. And lastly, of course, PI methane is where we set the methane concentration to the 1850 value. So why are we looking at these three? The PI air and PI ozone is quite obvious, because PI air means that we emit less SO2, and PI ozone means that we emit less ozone precursors. But why methane? Because when we look at the precursors, we look at the oxidants that SO2 react with, or methane actually affects the oxidant availability in the air. So let's look at the left plot first. So we see that the ozone mixing ratio, which is like roughly the concentration, keep increasing monotonically across the historical period, and that is denoted by the black line here. And when we fix the ozone precursor emission to the 1850, we can see that the ozone mixing ratio is constant over time. Or put it in another way, it means that from 37.5 ppb here to the 50 ppb here could be attributed to the ozone precursor emission. That's why there is the up arrow here. It means that ozone precursor emission increases the ozone in the air. Similarly, we can see that by following the historical methane emission, the methane actually contribute to the change in ozone mixing ratio. And this is because methane is a source for ozone production in the troposphere, and these are all the tropospheric oxidants. And in the middle plot would be the OH concentration. Again, we see that ozone precursor increases the OH concentration. That is because ozone is also increasing the oxidative power of the atmosphere. But conversely, we can see now for the first time that even though we decrease the amount of methane in the atmosphere, this actually increase the OH concentration. This is because methane is a major sink for OH, and by having less methane in the air, it means that the OH is not reacted away, mean that we have excess OH. I'll put it in another way. It means that the historical methane emission actually decreased the available OH concentration in the air. And the similar thing could be said for the hydrogen peroxide as well. So both ozone precursors and methane increase the hydrogen peroxide concentration. So now we have the picture of how the oxidant changes. Let's look at the oxidation, so how SO2 are formed. As said earlier, when we have SO2 plus OH reaction in the gas phase, we add new aerosol particles into the system. But the methane in the air actually decrease the OH concentration. So we have less OH. We have decreased OH oxidation in the air due to the historical methane emission. But the ozone precursor would add into the OH reaction. But even though, as summarized here, we see the increase in ozone mixing ratio due to both the ozone precursor and methane, we don't really see the increase in the OH oxidation, and this is because this channel is already saturated, so additional oxidant doesn't contribute to additional production. And finally, methane also increases the H2O2 oxidation. Now that we have the change in the oxidation, we will look at how this affects the radiative budget. So a metric that we use to study the radiative budget is called the effective radiative forcing, or ERF, and this is a measure, it's a comparison between a model with a normal emission and the model with one emission taken out, and then we see the change in the radiative budget at the radiation at the top of the atmosphere, and that is why the radiative forcing is in the unit of watt per meter square. But furthermore, we can decompose the effective radiative forcing into its smaller components to study the effect of aerosols. So we can look at the effective radiative forcing at the cloudy part of the sky and attribute that to the change in cloud radiative effects. Also, we can just look at the part of the model where we only have the aerosols cover, and we would attribute that to the aerosol IRF, or the scattering effect. And finally, we can look at the clean and clear sky. So there is no cloud cover, there is no aerosol overall. So this is just the clean global, the greenhouse gas effect. So let's look at our original experiment, just the aerosols. So we see that overall, aerosol contribute to a negative ERF. When the ERF is negative, it means that there is less solar radiation reaching going through the top of the atmosphere, which will contribute to the cooling. So if I could like make you remember something from this talk, it would be, if we have a negative radiative forcing, it means that we are cooling down the atmosphere, and the aerosol is overall cooling, and this is due to the change in the cloud radiative effect. What about ozone? So we are now looking at the change in this effect due to ozone precursors. So we look at the purple line first. So the purple line is the greenhouse gas effect, and we know that ozone is a warming gas, so it contributes to a little bit of warming, so around like 0.18 in the recent years. But if we zoom in, we actually also see that there is a change in the aerosol scattering effect, or the IRF, and this is around like 0.08, and that adds to a little bit of cooling from aerosol formation, and we can say that this is due to the additional aerosol we added into the system. This number may seem small, but if we compare to the change in directly emitting aerosol precursor, this is actually like 28%, so this is not negligible. And finally, we look at methane. Methane is a potent greenhouse gas. So we see that methane in the historical period, methane contributes to around 1 watt per meter square of warming. So that purple line is warming. But not only that, because also inhibit the aerosol formation, we also see the change in the cloud radiative effect. So ozone also inhibit cloud formation through the OH reduction. So we actually have a double warming effect here. And these are the change in the cloud property, which I will not go into. Furthermore, because aerosol is very regional, we also see a further regional effect due to the change in precursors. So ozone is actually cooling down, change the AOD regionally, while we don't see much change in the aerosol cover change due to methane, even though we see a little bit of change in the oxidation. And finally, I also highlight my new results here. So not only we see the change, we see the cooling from aerosols. Aerosol cooling also have a seasonal trend as well. So we see that aerosol only in this model, so aerosol only contribute to the cloud effect during the summer months. So this is a plot for months and the latitude, so we only see well, the warming only happen at the higher latitude and during summer months. So I'll stop my talk here. So the summary would be added the short-lived climate forces such as ozone and methane actually contribute to an additional relative effect due to the change in aerosol formation. Ozone adds to a little bit of cooling, so it would counteract its own warming effect. But methane adds another warming component due to the reduction in cloud cover. Thank you so much.
Thank you, Prin. That was really, really great talk. I think due to time, we are going to have to move on.
Oh, sorry.
No, you're totally fine. But I do encourage, if anyone's got any questions for Print, please leave them in the chat, and then Print, maybe you could answer any questions that come up in the chat. Thank you so much.